This is Dr. Holt. This video is on the AP Physics C exam. It's on the review, and we're going to be talking about the topic of gravity. We'll start with Newton's Law of Gravity. Now, Newton's Law of Gravity, you should know two basic formulas. The first one is the force of gravity between two masses is equal to big G. Now, big G is equal to approximately 6.67 times 10 to the minus 11th newtons times meter squared over kilograms squared. You're going to multiply that by the mass of one object in kilograms times the other mass in kilograms divided by the distance between the two masses squared. And I'll show that here on the next slide. Now, the other one you should know is that the acceleration of gravity is going to be very similar to this one, except we're taking out one of the secondary masses. So it's going to be big G, 6.67 times 10 to the minus 11th, times the mass, and the r distance here is the distance you want to go away from the centroid of that mass. That will give you the acceleration of gravity, or it's like a gravitational field at a certain distance away. Now, Newton's law of gravity, again, is based upon the r value being between the two center masses. It is not, let me repeat, not from surface to surface. You must find the center mass here to the center mass here. And again, by following that formula, we can calculate what the force is. Now, one thing to note, you have two forces. They're going to be equal and opposite. You're going to have a force going back this way, and you're going to have a force going back this way. These two are going to be the same magnitude, but opposite directions. So M1 is feeling this force from M2, and M2 is feeling this force from M1. I'm going to run through just a calculation here and talk about how to find the force. Here I have the mass of Earth as 5.97 times 10 to the 24th kilograms. The mass of the Moon as 7.38 times 10 to the 22nd kilograms. And I have an average distance about 3.844 times 10 to the 8th meters away. And I'm going to calculate what the force would be. To do that, I would just come back and follow this equation here. The force of gravity, and again, we'll do the Moon on the Earth. We'll do moon slash, meaning moon on the Earth. It's going to equal to 6.67 times 10 to the minus 11th. I'm going to drop my units here because it's going to hard to fit everything in. Times the mass, 5.97 times 10 to the 24th. This is the mass of Earth. Times the mass of the Moon, 7.38 times 10 to the 22nd. Now I'm going to divide by, in parentheses, this value right here. I'm going to calculate the distance between. Now again, remember, if you're given the distance from center to center, you need to add the two radiuses to that to get the actual distance from center of mass, center of mass. All right, here we go. 3.844 times 10 to the 8th squared. And again, make sure everything is in meters and kilograms before you run that. If you run that calculation, you will find that the force of the Moon onto the Earth is going to be a value of approximately 1.989 times 10 to the 20th newtons. Again, let me repeat, the force of the Earth onto the Moon is also going to be the same value, 1.989 times 10 to the 20th newtons. So as I show that again with vectors, I will have a force going this way, that the Moon is trying to pull the Earth this direction here with this force, and now the Earth is trying to pull the Moon. Now, if there's no velocity, no tangential velocity, you could find immediately what the overall acceleration is between these by just taking this force here, dividing it by the mass of the Moon. You can find the acceleration. It moves back this way, and same way with the Earth. You can find the acceleration by taking the force and dividing it by the mass. You would find out the acceleration. Obviously, if these two, the Earth and the Moon, are not rotating around a barycenter, then they would move together and come in contact. And again, obviously, since this has greater mass, it's going to accelerate to the right at a different rate than this. This is going to be a faster rate going back to the left as far as acceleration goes. All right, so that's a very simple problem, but that's how you find the gravitational force. We're going to work one more of these. I added another mass of a moon up here. This is a more of a two-dimensional situation. So what we want to do here, again, we want to find out what the force is between each of these. Now, we already calculated this. I did not change any of these distances here. So here I want to find out what force does the Earth feel as a result of these two moons. So we already know we have one force coming off this direction here, and we've already calculated that. And I'll just go ahead and write that down as 1.989 times 10 to the 20th newtons. And I'll circle that. All right. Now, one of the things I catch students trying to do here is they try to break the radius, or the distance from center mass to center mass, into a horizontal and vertical component. You do not want to do that. You want to find out what is the force along this center mass line. So I like to immediately draw a vector that goes back that direction here. So first thing I want to do is find out what that force is. And to do that, we'll call this moon 2. So the force of moon 2 onto the Earth is going to equal to, we're going to do exactly the same thing we did before. We're going to take 6.67 times 10 to the minus 11th times 5.97 times 10 to the 24th. Again, we're using this, and then we multiply it by this mass too. 7.38 times 10 to the 22. And now we're going to divide by, again, do not break this into components. Just take this value here and square that. 5.437 times 10 to the 8th. We're going to square that value right there. All right, let me just go back real quick. I want to make sure I did write that as square. Yes, I did. Okay. All right, so we're good there. All right, now we'll run that calculation, and I will find out that the force of moon 2 onto the Earth is going to give me a value of approximately 9.9412 times 10 to the 19th newtons. And obviously you expect that force to go down because you have a greater distance between. Alright, so again, that is that value right there. We'll move it over here and we'll put 9.9412 times 10 to the 19th newtons. Alright, at this point, if you want to find what the force is by these two, you're going to have to break this one into horizontal and vertical components. So what I will do here is I will sum up the forces horizontal. And when I do that, I will get 9.9412 times 10 to the 19th times the cosine of 40 degrees. Like doing the cosine, I'll get the horizontal component, plus 1.989 times 10 to the 20th. I will add those values together, and I get a value of approximately 2.7505 times 10 to the 20th newtons. Okay, and again, that's going to go back this direction here. Now I'm going to sum up the forces in the vertical direction. And when I do that, only one I have is this one here, which will be 9.9412 times 10 to the 19th times the sine of 40. And again, just to clarify, the reason I'm doing the sine of 40 because that's going to give me this vertical component of this vector as this force is going up. And when I run that calculation, I will get a value of 6.390 times 10 to the 19th newtons. All right, and I like to draw the vectors showing what direction it's going. All right, now at this point, to find out the actual force, we're going to use Pythagorean Theorem. So the actual force is going to equal to 2.7505 times 10 to the 20th. We will square that value there. We will add that to 6.390 times 10 to the 19th. We'll square that. We will take the square root of that value right there. And when we do that, we will get a value of 2.824 times 10 to the 20th newtons. All right, and that's what the actual force is that these two planets combined are causing on the Earth. Now, if you wanted to find out what the angle was going to be, so what I'm going to do here is I'm going to take these away and we're going to replace it by this particular force. And obviously we know it's going to go back in this direction here. Somewhere like here. Let's color that red so we can hit highlights. So this is the force. Now, if I wanted to get this angle here, call it theta. Again, that angle is no longer going to be 40 degrees. All I have to do is come down here and say theta is going to equal to the inverse tangent of my vertical component, which was this one here, 6.39 times 10 to the 19th. I will divide that by my horizontal component, which we said was this value right here, 2.7505 times 10 to the 20th. When I do that, I will get theta of approximately 13.079 degrees. And that would be that angle right there. So now, if nothing was like spinning around a barycenter, then I could find out immediately what the acceleration of this object is in this direction by taking whatever this force is, divide it by this mass. That would give me the acceleration, and it'd be traveling at this angle of 13.079. Okay, in Newton's law of gravity, the equation we're going to use is the acceleration of gravity is going to be g, 6.67 times 10 to the minus 11, times the mass of this object here, and we're going to divide it by the radius squared. And radius squared is a little misleading. You can call it distance squared if you prefer. We're talking about what is the distance from the center out to this point here. This distance here is what I would use if I want to find out what the gravitational acceleration would be at any point along this dotted line here. I would use this distance here. If I want to find out what it is here, I would use this distance here. Vice versa, I'm looking for this distance, obviously I would come all the way out to this distance here. So even though it's typically written as r squared, we're talking about the distance from center of mass out to a point beyond the surface of the object itself. We can find out what the gravitational acceleration will be at those points by just taking this equation here. Alright, I'm going to base this on, we're going to look at Earth for a second. If I want to find out what the gravitational field would be, or the gravitational acceleration would be, let's say at the surface, let's say someone standing right at the surface here. I'll run that value using this equation here. So the acceleration, gravity, is going to equal to 6.67 times 10 to the minus 11th. Again, I'm not going to include my units just because the problem would really spread out. Times the mass of Earth, which is going to be 5.97 times 10 to the 24th. I will divide that by the radius squared. I'm going to just do that. Let me just show where the vector is. The radius. The radius is going to be from here to there. That's going to be what we're going to be using. That's from center of the Earth out to the outer shell. We divide that value by 6,371. It's 6,371 kilometers. So I'm going to multiply that by 10 to the third. I'm going to square that value there. And if you run that calculation, you will find very quickly, look what you get. You get the 9.81 meters per second squared. So in physics, when we talk about the acceleration of gravity being 9.8, we're talking about at the surface. And again, it's all based upon just this equation here. That's where this value comes from. Now, one of the things that's kind of interesting and confusing, let's talk about what the acceleration of gravity would be at the International Space Station. Now, the International Space Station has been in orbit, I believe, since 1998. And it circles the Earth at a radius of approximately about 200 miles above the surface of the Earth. I'll do it like that. So we'll put a little blank here, and we're going to say this little dot here represents what the where the space station would be. We'll call that space station, IS, International Space Station. And I want to find out what the gravitational value would be, or gravitational acceleration would be at this point here. Again, I am a distance of approximately 200 miles, or we convert to 200 miles, that's about 322,000 meters, just approximately. Okay, above the surface of the Earth. Now, if I want to find out what that value is going to be, I will find the acceleration of the gravity of the International Space Station. We will take 6.67 times 10 to the minus 11th. Again, we will multiply it by the mass of the Earth, 5.97, times 10 to the 24th. Now, when you do this division, do not just use 322,000 meters. You need the distance from the center out to this. So I'm going to take 6371. I'm going to add 322 to that, and then multiply that by times 10 to the third, and then I'm going to square that value right there. Now, the interesting thing is, often the general public is misinformed or confused, and they think, well, the people around the International Space Station are weightless out here just because it's so far from Earth. If you calculate that value there, you will get a value of about 8.89 meters per second squared. So you'll find out the acceleration of gravity is about 90% of what it is at the surface of the Earth. So it's much different than what people anticipate it would be, or speculate what it would be. Now, notice this equation. Since you're using this equation here, if you wanted to find out what the gravitational force would be at anywhere along a field line, all I have to do is I'm going to do one more curve here. I'm going to take this back out to here. Let's say, that's a little crooked. Let me move it over, kind of get it straight. If I want to find out exactly what the gravitational force would be between these two objects here, all I'd have to do is, if I knew what the gravitational acceleration would be, or the gravitational field at this point, all I have to do is take this mass, multiply it by this value here, and look what happens. If I take that value here, multiply it by, say, mass 2, multiply this by mass 2, mass times acceleration gives me the force. So I hope you see the relationship between gravitational field and gravitational force. It's just, if I include another mass here, I get the original equation we talked about. Alright, anyway, I hope this video was useful. Pretty much goes over Newton's law of gravitation and just talking about the force of gravity and the acceleration of gravity.